Transforming functions, graphing functions, important features of graphs. So this is the first lesson in this new chapter, Transforming Functions, and I'm going to discuss the important features of graphs and especially the graphs which are unknown to us. So let's start with this diagram here. We have common families of functions, and you should be by now familiar with all of them. First, there is the family of linear functions in the form f y equals ax plus b, where a is not equal to 0, so you'll know that the graph of each of such functions is a line, and hence the name of the family of the functions. Now there were the quadratic functions, y equals ax squared plus bx plus c. Also there was this condition a not equal to 0. Cubic functions, well, we have not spent much time with cubic functions, but there are a reasonable generalization of the quadratic functions. In addition to these three terms in quadratic functions, there is the cubic term there, and well, if you encounter them, then you will see what their graph looks like. It's almost similar to parabola, but there is a very different feature which ensures that one of its branches goes to or approaches negative infinity in the vertical direction, and one of its branches approaches positive infinity in the vertical direction. So, well, but I don't need to talk too much about this one. Power functions, you may remember these. Y equals x to the power of n, where n is an integer. Exponential functions, y equals a to the power of x, a is positive and a is different from 0. Logarithmic functions, which were the inverse functions to exponential functions, y equals logarithm of in base a of x. These were the conditions required for a. There was also a very similar category of functions, y equals natural logarithm of x, or we could use y equals decimal logarithm of x. Okay, so all of these would fall into this category of logarithmic functions. Then we talked about the reciprocal functions, y equals k over x, k is different from 0, and you know already that the graph of this consists of two branches of hyperbola. Okay, now the rational functions, we didn't study the general situation for rational functions. We just tried to describe this subcategory of rational functions in the form ax plus b over cx plus d. These were the conditions, and you already know that there is a relationship between this family of functions and the reciprocal functions, since there is a deep connection, and one can show that when you translate a reciprocal function by some number of units in the horizontal direction and then in the vertical direction, you may end up with this form of a rational function. Okay, so all of those functions were interesting, and we should be able to sketch their graphs just by drawing upon our knowledge about their characteristics, which should be available to us. But there are also some other functions, and this is what I'm going to talk about later on. But before I do, let me discuss for a while important features of graphs. So anytime you draw a graph, you need to describe its important features. You need to label interesting points, show them on your graph, and describe their characteristics. So first, what is interesting for us for each graph are the axis intercepts. So the graph may have only x-axis intercept or only the y-axis intercept or none, but anytime it does, we need to include them. Now, well, what does it mean to include them? It means that you just label this point and include its coordinates, okay, in your picture. Now, turning points. Well, this is something which has to do with the monotonicity of functions. So you may have the function which is strictly increasing on some interval like this, for example, and then in one point it starts to be strictly decreasing. So this point in which it changed its character from strictly increasing to strictly decreasing is called the turning point, and vice versa. You can have the function which is strictly decreasing and then all of a sudden it becomes strictly increasing like this. So this point here would be also the turning point. Turning points are of two different kinds. So you have either the local maximum, as here, this point here would be the local maximum, and this one would be the local minimum. The name local has to do with the fact that the function may have another local minimum, for example this one here, and both of them are local minima, but only one of them is the minimum of the function, and namely this one, because in this the function values assume larger values, so it's not actually the minimum of the function. This might be, okay? So there is a slight difference between local maxima and local minima and minima of function. Local maxima have to be maxima of the function in a local set of values, I mean in a local domain in the vicinity of a given point. Okay. Now, another characteristic which is important are the values of x for which the function does not exist. So sometimes this happens that the function is not defined for a given point because, for example, you would have to divide by 0 if you had to evaluate its value at that point. So these are interesting. Usually these points might have to do with another feature which is called asymptotes. So usually when the function is not defined in a given point, usually, it's not the rule, but usually there is the vertical asymptote. Also there can be horizontal asymptotes. So it's the asymptotic behavior of the function that is interesting, so we should always describe it. Okay, now let me talk a little bit about unfamiliar functions. So what does one do if he or she wants to investigate the unfamiliar function? So sometimes the function doesn't take any of those forms and it's different, and you need to investigate its properties. So the most simple way how to do it, but also the most time consuming, would be to investigate them by hand using a suitable table of values and a graphing paper. So imagine you would set up the table and choose x values quite close one to the other and fill in the table by using the calculation, by using the formula of the function, and then you would just plot this table on the graph, on the graphing paper, and then perhaps you could see the typical or important features of the function, because you could then fit these points with a curve of some shape, and you could then describe the function. But this, as I said, is quite time consuming, and one would not do it nowadays. So perhaps a better idea is to use technology. There are many different possibilities. I'm going to use Geogebra in this course, but of course some people may have graphing calculators, or you may use other software suites for this. But Geogebra is free, so why not use it? So if there is no domain specified, because sometimes it's not, you have to start with a large viewing window to ensure that you don't miss any interesting features. So that's why it's always a good idea to zoom in and zoom out in Geogebra to see if there is some surprising feature in the graph. So I will talk about it later. Okay, now let me finally describe the slight difference between these two words. If you are asked to sketch versus draw the graph. What is the difference? So if we are asked to sketch a function, our figure should show the graph's general shape and its key features. It doesn't have to be very precise. It doesn't have to exactly pass through the points calculated using the formula describing the function. It has to be qualitative. Okay? So if we are asked to draw a function, our figure should be done more carefully and to scale. So this time we should really be very careful. It should pass through all the points which can be calculated using the formula of the function, and it should be quantitative hence. Okay, so now let me give you an example of investigation of such an investigation of a function which is not familiar. So example 1, consider the function y equals 2 to the power of x over x minus 2. Use technology to help answer the following. So in part A, find the x-intercepts, then we have to do other things. So turning points, asymptotes, state the domain and range, and finally sketch the function showing all its key features. So let me now show you the easiest but the most time-consuming way how to do it. So I have prepared a Geogebra Classic application for you, and now I will show you how to do it there using the table of values. Okay, so just what I need is I need to add table view to this, or spreadsheet view to this window. So I will just choose spreadsheet like this. Okay, now I have the this part which shows me the algebraic view. This is the graphing view, and this is the spreadsheet view. Now I need to set up the table for this function. So let me start with the number -4 as the first number, and then I will go with the step of 0.4. So the next one would be -3.6 like this, and I need to continue until I reach number 4. So therefore it's good to copy this table, or these two values, and copy them according to this pattern. So I hope I will get to number 4. Okay, here it is. So I will just delete the rest. Now I will use the formula here to calculate the function values. So use the equal sign, 2 to the power of. Now instead of x I click here, so I have the cell A1 and A1 in a table, and then I have to divide by the same cell, and I have to subtract 2. Okay, so this is the formula, and I got the first value. So I'm cheating a little bit here, because what I do is I'm asking the computer to do the calculations for me. If you had no computer, and if you had just the pen and paper and calculator, perhaps you would have to calculate each of those values separately, draw your table, and then plot these points to your graph. So if you want to plot a table to a graph in Geogebra, what you do is you highlight the table and use this button here, click on it and tell it to draw or create a list of points. Okay, now I just confirm, create. Here are my points. These are the points in the list. Okay, you see that the program labeled them, and it's not very practical to have names assigned, so perhaps it would be a good idea to highlight all of those points and choose not to show the label. So I will hide the labels, okay, like this. Okay, so these are the points of the graph, and you can see something shows up here. It looks like the curve would go like this, and also here perhaps it would go something like this. Okay, so now if I tell Geogebra to use a different way to plot the function, and the different way is just I give it the formula, so I input here y equals 2 to the power of x divided by x and subtracted I subtract number 2, you see that the GeoGebra just drew the graph right away. Okay, so the basic idea how it does it is that it calculates the function values, but for much more many points and than I did here in this table, and thus draws a nice curve. It's not just these points, but a lot more. Okay, so the GeoGebra can do it much better even without the table. So the table step can be skipped altogether, and you see the function like this. Okay, so now there is a slight difference here. If I don't have GeoGebra Classic, and this is your situation when you have just your smartphone, there is no GeoGebra Classic there, and there is not this possibility, as far as I know, to create tables. You may use just a simple graphing calculator in GeoGebra. So here I have the graphing calculator in GeoGebra. It looks somewhat similar, but there are slight differences. It's designed in such a way that students can use it in exam conditions, so it doesn't allow them to do so many things as the usual GeoGebra Classic application. So some of its features are reduced, but what it does allow you to do is to input the function. So I will do it again. Y equals 2 to the power of x over x, and now minus 2. Enter, okay, and here is my function. This is what I get when I have a graphing calculator, for instance. So this is the graph. I can see the basic features of the graph here, and it gives me these 3 interesting points. This point and this point are x-axis intercepts, and this one is the turning point. I can click on it and it tells me, yes, this is the turning point. It has the coordinates 1.44 and minus 0.11. Okay, now this point here is the root, or the x-axis intercept, and this one is also the root. I can zoom out to check whether there is nothing interesting outside of my scope. No, there is not, so I can go back to the original view, and this would just be it. I drew the graph of the function using the technology, and now what I need is to go back to the presentation and answer these questions in the exercise. So let me do it. So find the axis intercepts. So let me write it down. This is part A of this exercise. In part A I have the axis intercepts. So there were only x-axis intercepts. Okay, and these were, the first one was the point 1 and 0, and the other one was the point, as far as I remember, but let me check it, it was 2 and 0. Okay, it was 2 and 0, like this. So these were the axis intercepts. Or I would just say that the x-axis intercepts were just the numbers 1 and 2. Okay, so there are 2 ways how to understand what the intercept is. Now, in part B, find the turning points of the function. So there is one turning point, turning points. So there was just one, and it had the coordinates, as far as I remember, but let me check it. It had the coordinates of, let me click on it. No, it doesn't work. I have to make it larger. 1.44 and minus 0.11. 1.44 and negative 0.11. So this was the turning point. There was the local minimum in the function. Okay. Now in part C, find any asymptotes of the function. So let me go back. You see that there is the vertical asymptote, and it's the y-axis itself, and there is the horizontal asymptote passing through negative 2, because as x approaches negative infinity, y approaches negative 2 from below. So I may write it here. So there is the vertical asymptote, which is just x equals 0, so it's the line, and there is the horizontal asymptote, which is y equals -2. Okay, state the domain and range of the function. Last the part D. State the domain and range. So the domain of the function. Well, it seems that it consists of all real values except for the value of 0, for which it's not defined, and it is reasonable because if x is 0, you would have to divide by 0. Okay, and this is in line with what I had said previously, that whenever you have division by 0, there is the vertical asymptote at this point. Okay, so I can say that the domain of the function is the union of two intervals from -infinity to number 0 excluded, union from 0 to +infinity, like this. Now, before I go to part E, I have to include also the range of the function. Range of the function. If you look at the graph, there are all y values from -infinity to -2, and then the values starting at -0.11 here to +infinity. So let me include it. So we go from -infinity to -2. Okay, -2 is excluded. Union, and oh yes, and then from -0.11 to +infinity. This number here is included in the interval, and the reason for that is it's the local minimum. So this value is assumed by the function at that point. Okay, okay, and finally we have to sketch the function showing its key features. So let me first label the axis. This is the y-axis, this is the x-axis here. I have number 1, number 2 here, and there is the local minimum somewhere here, and the function should pass through this minimum, through this point, like this, and also through this, and should have the vertical y-axis as the asymptote. And there was another feature, there was this horizontal asymptote which passed through -2, so let me sketch it. So this line here is y equals -2, and the function should have it as its own asymptote and should approach this vertical asymptote like this. Okay, so this might be the sketch of the graph. It's not very precise, it's just qualitative, but it shows all important features. It shows the x-intercepts, it shows the turning point, and the turning point should be included by its coordinates, so I still have to add it here. So it's 1.44, comma, and -0.11, like this. So this is the turning point, and well, there is the equation of this asymptote, and the y-axis is x equals 0, it's the vertical asymptote. So this would be it. I showed you how to use Geogebra, both versions, I mean the classic version and also the graphing calculator version. Perhaps you should always choose the graphing calculator one because you have it on your smartphones, and this is how you do it when you have a function which is not the familiar one, so the function that you cannot describe in terms of familiar functions. But of course, this is not how mathematicians do it. They use more advanced mathematics called calculus to analyze functions, and they can do it even without technology. But this is far beyond our reach at the moment. So this is for you, waiting for you in the future when you study mathematics later at the university level.